right, page 160. Asked you to do number 17 for homework last night. A proof in some ways similar to proofs that you may see on tomorrow's test. If we have time at the end of the hour, maybe do a little bit more proof review, but we've spent the last few days reviewing proofs. So today's review lesson is going to primarily focus on the non-proof elements of tomorrow's test. Page 160, number 17, if you would, go and hold up the homework so that I can see that you did attempt it to the best of your ability. Where's the home? Oh, there it is. It's on the back of that. And then Genesis, that looks like it right there. And yes, all right, the only thing that would help there is, of course, if you'd written at the top of the paper what we had. Let's go and take a look at the picture. First of all, we're given a circle called O. We're given a diameter passing through O. We're given a chord that is perpendicular. Clang! We'll come back to that. CD. Hopefully you got that clang. If not, I don't think you could have done the proof at all. You had to get that clang. You were given any random point in arc CB. They happen to pick a point closer to B, but it really could have been anywhere. Point E. They had a chord drawn from A to E, A to C, C to E, and they called this point of intersection F. All right, so there's our picture. Obviously, your first statement should have been the given, where you wrote down a circle O, diameter AB, CD is perpendicular to AB. Did I mention clang yet? I don't know that I necessarily even need to mention E as any point in arc CV. F is the intersection of A and CD. I'm lazy. I'm going to skip that. That's
it didn't say to put circle O in the given.
It didn't. All right. Okay. So anyway, given. Let's get our clang. We have a chord perpendicular to a diameter, or better yet, better way to put it, we have a diameter perpendicular to a chord. And anytime a radius or diameter is perpendicular to a chord, class, it bisects the chord, and the arcs it intersects. So, number 2, if CD is perpendicular to AB, then AB is going to bisect CD. Now, interesting, they didn't actually label this point, because I don't care for a change that the chord is bisected. I care that the arc is bisected, and this arc is bisected. Now, I did tell you at the end of the hour yesterday, so I was giving you the homework, you're going to need to go all the way back to section 3.5 for your clang. So if you went back to 3.5, I'm not sure how you missed theorem 35, a radius or diameter perpendicular to the chord bisects the chord and the arcs. Now, if you did call this point P, for instance, and you happen to say that CP equals DP, okay, fine. Mainly, we're looking for arc CB is equal to arc DB, and arc CA is equal to arc DA, because a diameter perpendicular to a chord bisects the chord, and the arcs it intersects. How many did get the clang of bisected chord? You don't really care about that. Bisected arcs. All right, if you didn't, get it in now, because I don't know how you could have possibly done the proof without it. That's really the only clang we've got in this proof as far as I'm concerned. Let's look at what we're trying to prove. I'm trying to prove that angle ACE is equal to angle DFE. Now, while you may not have gotten the whole proof correct if you missed this key clang statement, every clang statement generally key, DFE is right here. All right, you could have still gotten some parts of this correct because you're trying to prove a couple angles equal, right? And as I look at these two angles, I'm like, all right, What kind of angles we got? Let's start with ACE. What kind of angle is ACE, Genesis? And an inscribed angle. So we could say that ADBE, right? And I'm going to use all 4 letters because it is a major arc, isn't it, class? It's bigger than the semicircle, so I need to use multiple letters. If I just said AE, that would be implying the ACE arc, and it's ADBE. And we know that an inscribed angle equals half its arc. How many did have that statement? The inscribed angle equaling half its arc. Okay, good. Now let's take a look at the other angle. Angle DFE. What kind of angle do we have at DFE, Quentin? It's in a circle, formed by intersecting chords, and I know that then must equal okay. So I could state, number 4, that angle DFE equals
half of arc DB.
What is its arc?
Or D.
DBE or DE, but well, I'm going to say DBE just to be consistent with what I had before, equals half of arc DBE plus
Half of arc
CA, which would be the vertical angles arc, or AC. Because this one isn't quite as quick and easy to write, but
an angle inside a circle equals half the sum of.
well, an angle inside a circle by intersecting chords, because you can get angles inside circles without intersecting chords.
Equals half of its arc. Half the sum of its arc.
Equals half the sum of its arc and
Arc. No.
so it has its own intercepted arc, but also it's the sum of 2 things. Its own intercepted arc, which is DB, and the arc that is the arc of the vertical angle. And its vertical angles arc. Something like that. All right. That's kind of clangy, by the way. If you look at the proof and you're asked to prove some angles equal, or in the course of putting your analysis together, you realize you need some angles equal. In a circle, it's, well, what kind of angle is it? What's it equal to? Now, if only there were a way to get that and that to be the same. Because ACE and DFE are both equal to half of, and if only those pieces right there matched, then ACE and DFE would have to be equal, right? So let's think. How could I get ADBE to be the same thing as DBE and AC? Chris?
No, I have a question.
Question, okay.
So in my proof, the way I did it, I think I went off on the next step because I said that angle DFE would also equal CB and AD added together, but now that I see that it isn't the angle, which I guess I was thinking it was CPB, but it's not.
I don't know. Ethan, you had a thought you wanted to share, it sounded like.
Couldn't we say that whole equals sum of its parts?
Okay, so we could say number 5. Which whole are you talking about?
ADBE.
Yeah, this whole arc, ADBE, has a whole lot of pieces and parts, doesn't it? And so as I could say the arc ADBE. Now, look at what my ultimate objective. My ultimate objective is to make it match this. But for now, what parts is it equal to?
AD plus BD, or DB.
Well,
Or DBE.
I would go with all of DBE as one collective because it's all one collective here, right? So let's say DBE, because the whole equals the sum of all its parts.
Well, then you can just subtract.
Kendall? Kendall? That clang's important. If you didn't have that clang, you're not going to be able to finish this proof.
CA equals DA.
Yeah, since CA equals DA, the number 6, I could restate number 5 how, Kendall?
Or ADBE equals AC plus DE plus DBA.
Right, so just restate exactly what you just said, but instead of saying AD, say AC plus DBE by
Substitution.
and so if ADBE is AC plus DBE, then right here where I see DBE plus AC, class, I could do another substitution and just put ADBE, right? I mean, this is that, right? So I just plug it in. And now by a second successive substitution, arc D, or angle DFE could be said to be equal to half of ADBE.
Oh.
And so therefore,
How does that work?
okay, Chris.
I am overthinking it, I know, but
No, you're not thinking it. That's the problem. ADBE is literally AD and DBE, right? That's whole equal sum of parts. But AD and AC are equal because of the bisected arcs. So instead of AD right here, we went AC right there with the sound effects. Very important. Well, this is that, right? They're right there. So if this equals that, then this goes right there. And now we get this statement. And if ACE and DFE are both half of ADBE class, they are equal to each other. By yet another substitution. So what we wanted to prove by a final substitution. You could also say halves of equals are equal. You could also say quantities equal to the same quantity are equal to each other, but substitution works just fine. So back to back to back substitutions here. And it finishes the proof. I don't know that you can do it without getting that bisected arc, though. You had to have those two pieces equal to each other. So, gotta get that clang. All right, gotta get that clang. Questions on the proof. Did anyone pretty much nail it? Okay, nobody. Does it make sense now?
Yeah.
Any other questions before we move on to the rest of our test review?
That. I didn't have it.
All right. Yeah, and I don't, again, you get this far and you're like, now what? You're like, man, I sure wish AD and AC were equal.
that's always my problem.
They are.
I always get to the middle and then I can't finish.
All right. Well, again, sometimes we need to get the clang at the beginning, right? And to get those clang statements in there.
I had to
All
do
right.
my-
Set your books aside. Set your books aside. Just have some paper out, and let's get reviewing for your test tomorrow. Some things to write down. Your test is going to cover pages 137 to 161. 137 to 161. Pages 137 to 161. In your textbooks, that's sections 3.5 to 3.19. That's sections 3.5 to 3.19. In your notebooks, that's theorems 35 to 46. Theorems 35 to 46. Okay, so 11, I can't count. 11 theorems with their corollaries covered here. Some terms and definitions, but it's not a term definition heavy section. necessarily. There are some terms like secant class,
The line that cuts through the circle and has a
twice, right? Line that cuts a circle twice. Tangent, touches once. Segment of a circle is the region bounded by chord and its arc. So the region bounded by curved on one side, flat on the other, okay? So that would be a segment of a circle. Any angle inscribed in a semicircle is a right angle. Any angle inscribed in a major segment, acute angle. Any angle inscribed in a minor segment, obtuse. Of course, that's not terms definitions. Trying to think of terms definitions here. Tell you what, I'll flip back real quick and make sure we cover all of those terms. And there weren't a lot in here. If you were to draw a polygon that is completely consisting of chords, picture it, a polygon that is made up of all chords of a circle, it would be inscribed. A polygon completely consistent of tangents would be circumscribed. So those are some terms that are there. The chord drawn between points of tangency for two tangents to a circle. The chord drawn between points of tangency of two tangents drawn to the same circle.
Common chord.
Chord of tangency.
chord, yeah.
Chord of tangency. Now, common means shared, right? Nothing's being shared here. A common chord would occur when two circles intersect each other. Now this is a chord in each circle. That's common chord. You see the difference between chord of tangency, common chord? And the line of centers would be a line that goes through the centers, right? So circle, here's a circle, there's a center, line of centers. Specifically, the segment between the centers would be the center segment. So again, those terms just make sense. Circles that have the same center.
Oh,
Not concurrent, not congruent, concentric. Concentric. Circles that have the same center, concentric. That's just about all the terms definitions. So like I say, not a terms heavy section at all. Mostly theorems, right? A few things in class notes. We did mention that if you were to inscribe a trapezoid in a circle, it has to be isosceles. If you were to inscribe a parallelogram in a circle, it has to be a rectangle. Okay, so those are, I think, some of the only things we put in class notes. You might peruse those. As I kind of flip through here, I'll see if I can see any other class notes type statements. They're usually asterisk problems from the book. Oh, there are a couple things. At a point on a circle, how many tangents? One. From a point outside a circle, how many tangents? Two. From a point outside a circle, only two tangents can be drawn in the circle. What will be true about those two tangents? They will have to be equal. If you were to draw two tangents to the same circle at the ends of the same diameter, they will be parallel to each other. That might be about it as far as class notes. So again, theorems, corollaries, those are the big ones. Arcs and angles, of course, is going to be huge, right? Practicing with arcs and angles, there will be a large section there on the test with arcs and angles question.
Historically, how hard is this test?
Well, every class is different, so historically may not work well. It is historically easier than the others, primarily because students study hard for it.
Why would they study harder for this one?
Because they did so bad on the last one.
Last one was my best one.
Last one was my best one.
All right, so anyway, so without looking at the side, because it won't be up tomorrow, an angle formed by two radii is equal to its arc, because it's called a central angle. An angle formed by two chords intersecting within a circle.
No, equals some
Half the sum of its arc and the vertical angle's arc. That's what we just looked at a minute ago in the proof. It's not up there anymore. An angle formed by a secant and a tangent intersecting outside a circle. Half the difference of the two intercepted arcs. An angle formed by a chord and a tangent.
half the difference.
Half its arc.
half its arc. An angle formed by two chords meeting at a point on the circle.
Half the sum.
Half its arc, we call it an inscribed angle. An angle formed by two tangents.
Half the sum. No, half the difference.
Half the difference of the arcs. An angle formed by two secants.
Half the difference.
Half the difference of the arcs. Memorize them. Know them. Think about them. Now, of course, it's harder because you're answering an out loud question, whereas on the test you get a chance to read it and then reread it. Now, let me say it again. You get a chance to read it and reread it and draw it. So take the time to read it, reread it, and draw it. Right? Take your time to think it through before you just slap an answer down. Okay, so since you have that opportunity, take advantage of it. Yes, sir.
Is there going to be any always, sometimes, never?
You'll find out. All right. Let's review some things from our theorems and corollaries we just have to know. A diameter or radius that is perpendicular to a chord bisects the chord and the arcs that it intercepts. Okay, a diameter or radius that is perpendicular to a chord bisects the chord and the arcs that it intercepts. If a diameter or radius bisects a chord other than another diameter, it'll be perpendicular to the chord. If a diameter or radius bisects a chord, it will be perpendicular to the chord. The perpendicular bisector of any chord will pass through the center of a circle. Chords that are equidistant from the center of a circle are equal. Chords that are not equally distant from the center of a circle are not equal. The chord that is closer to the center is greater. The chord that is smaller must be further away. I asked this already, but I'll ask it again. A polygon with all sides tangent to the same circle.
Rectangle. Wait, tangent? No, circumscribed.
Circumscribed polygon. A polygon with all sides tangent to a circle is a circumscribed polygon. The circle is said to be inscribed. A polygon, all of whose sides are chords of the same circle,
Rectangle.
is an inscribed polygon. And therefore the circle would be circumscribed. What is the longest chord that may be drawn in a circle?
The diameter.
Diameter. What do we call a line that touches a circle only once?
Tangent.
Tangent. Clang response to tangent, though, is that a tangent is perpendicular to a radius or diameter. Tangent is perpendicular to a radius or diameter. So tangent and radius together, perpendicular, right angles, all that fun stuff. At a point on a circle, how many tangents? One. How many tangents from a point outside a circle? Two. I already asked so many of these. Tangents drawn from the same point to the same circle. Equal. How many tangents at the ends of a diameter?
One.
Are parallel. The line that joins the centers of two circles.
Line of centers.
Line of centers. A line that joins the points of intersection of two circles. Common chord. Line that joins the points of intersection. Again, drawing pictures for these on the test would be helpful. We know that if you were to draw the line of centers for intersecting circles, the line of centers will be the blank of the common chord.
Perpendicular.
The line of centers will be the perpendicular bisector of the common chord. That's one of our theorems. Make sure you know that one. Circles that have the same center. Concentric. A line that intersects a circle at 2 points. Secant. Region of a circle bounded by a chord and its arc. Segment. Any angle inscribed in a semicircle?
Right angle.
Right angle. Angle inscribed in a major segment. Angle inscribed in a minor segment. Obtuse. Arcs of a circle intercepted between parallel lines are equal. Remember, that would be if you have a circle and you have parallel lines, these arcs intercepted between them. Now this is technically an intercepted arc. This is an intercepted arc, but the arcs in between the lines would have to be equal to each other. All right, let's practice with arcs and angles one more time in preparation for your test tomorrow. On your paper, go ahead and draw a nice big circle, or your best attempt at a nice big circle. Easier said than done, I know. We're going to pretend that's a circle. It's a perfect circle. We're going to draw a diameter through the center point O. We'll call it AB. Oh, let's see here. We're going to draw another diameter through the center point. We're going to call this CD. We're going to draw a tangent line at C. We'll call it PCX. And draw a line from P all the way over to B. And through this point of intersection, which I will call M, we'll draw another chord, call it AMF, and let's join C to F. Finally, let's connect A to D and B to D. There's a whole lot of fun stuff going on here. All right. Given that AB and CD are diameters, given that arc BF is 65 degrees, given that arc EC is 20 degrees, where's E? Oh, that's this point. Sorry, there's that little point on the circle. Given that arc EC is 20 degrees, given that arc AD is 105 degrees. I want you first of all, of course, to find all the missing arcs. AE, BD, CF. Also want you to find the following angles. AOC, BOC, BAD, ABD, ABE, Chick-fil-A, CMF, EMA, BMD, EBD, BPX, FCX, and DCP.
Okay.
All right, go.
10 minutes.
I know we got plenty of time.
let's go ahead and take a look at these together. And the first arc we needed to find was arc AE. Keep in mind, CD being a diameter class means that CD being a diameter means that CEAD is a semicircle, therefore 180 degrees. I've already got 105 and 20. That just leaves this one to be 55 degrees for
size.
that one there. And again, not drawn to scale, right? I mean, this big one is 20, this tiny one's 55. Okay, we don't trust our eyes, right? How many got 55 for AE? All right, then BD. Well, if we consider that arc or diameter AB gives us another semicircle below it, we've got 105 here. That leaves 75 degrees here. And then for CF, we could look at either this diameter and this semicircle. We say, well, I've already got 140 degrees used up here, so that only leaves me with 40 more. Or you could do the same thing above AB and say, well, I've got 55 and 20, 75, I go 65 here, that's still 140, leaves me with 40. Again, clearly not drawn to scale, but how many did get 40 for arc CF? All right, so if you're good on all three arcs, raise hand. All right, which one?
CF, I got 60.
CF got 60. Okay.
So that's gonna throw off mine.
That is going to throw off some of your answers. All right, so I'll try to keep that in mind as I go. All right, let's start with angle AOC. And could have gotten that one, right? Chris would have gotten that one correct as well. It's a central angle class. It's equal to its arc. Its arc is 75, so it is 75 degrees. Now, BOC, Chris, you would have missed if you put 60. You would have had 125 here?
Yeah.
Okay, well, we should have had class 105 for that one. All right, for BAD, what type of angle class? Inscribed angle equals half its arc, so it's going to be 37 and a half. Or 37 degrees, 30 minutes. All right, angle AB, I keep trying. Angle ABD is over here. Another inscribed angle, again equal to class half its arc, so it must be 52 and a half degrees. Now, another way we could have looked at this, and don't want to get ahead of myself, but I don't end up asking this one. If this is a diameter class, then this is a semicircle, which means this angle is inscribed in a semicircle, which means it is a right angle, which means that this is a right triangle, and the two acute angles of a right triangle are complementary.
Yeah.
Two acute angles of a right triangle are complementary. So I could have just gotten the complement, right, which is 52 degrees, 30 minutes. All right, anyway, angle ABE, this little guy right here, another inscribed angle, again, half its arc in this case, 27 and a half degrees. The Chick-fil-A angle, CFA, here we go. Another inscribed angle, going to equal half its arc, going to be 37 and a half because it cuts off that 75. Angle CMF, right here where the M is. The M is kind of in the way. This angle is not central, it's not inscribed, it doesn't have a name, but it's formed inside the circle class by two chords. It's going to be half the sum of the arcs. How big is its own arc? 40. Now again, Chris, on this one you'd have had 60, so your answer is going to be off by 10 degrees when it's all said and done. The vertical angle is here. Its arc is 105. So the sum of the arcs is 145. Half the sum would be 72 and a half. Chris, you'd have had 82 and a half. Am I correct?
I had 87 and a half. No, wait. No, CFA, or CMF is what we're on?
Yeah, CMF.
I had 87 and a half.
All right, should have been 82 and a half because you would have had, you said 60, right? 60 and 105 is 165 divided by 2 is...
Yeah, I guess I must have added it wrong.
82 and a half. All right, so EMA next up. Emma, EMA, this little guy right here. Again, inside the circle, class equals
sum.
Half the sum. Its own arc is 55. The vertical angle's arc is 65. The sum is 120. Half of that is 60 degrees for Emma. BMD, right here, its own arc is 75. The vertical angles 20 degrees adds to 95. Half of that is.
Where's everyone?
All right, EBD, that's this whole angle here. Now, if you wanted to, if you happened to write in that ABD was 52.5, and you happen to write in that EBG, or ABE later was 27.5, then that could give you, just add them together, right, to get your 80 degrees. Or you look at the whole thing, its arc comes from here to here, total arc of 160, half of that is 80. So either way you wanted to approach it, 80 degrees, your angle. BPX,
That's not what I got.
that is not what you
I
had.
got 52.5. I must have left out an angle.
Yeah, so if you looked only at this part right here,
Okay.
and the angle cuts off from here to there, so you just left off the 55 portion of it. All right? BPX is outside the circle. Secant and tangent, class.
Half the difference.
Half the difference. Now, the first arc that these lines cut off is right here, 20 degrees. The next arc that gets cut off is right here, 105 degrees. The difference of 20 and 105 is 85, and half of that is 42.5 degrees. Or, Chris, in your case, you'd have had 125, 105, 52.5. Okay. All right. FCX. FCX is an angle formed by a
Chord and tangent.
chord and tangent. It's going to equal half the arc. Its arc is 40, so we should have gotten 20. And Chris, you'd have gotten 30.
Yeah.
And DCP. DCP. It's a diameter and a tangent. What do we know about a diameter and a tangent at the point of tangency? Perpendicular. So 90 degrees.
That's not what I got.
Or you could look at DCP as cutting off at D, and here its arc is 20, 55, and 105 adds up to 180. Half of 180 is 90. But it's easier if you remember that a tangent is perpendicular to a diameter at the point of tangency. Did anyone get all of them correct? You were perfect. Ooh, how many maybe just missed a couple?
I didn't see CM there.
Okay, didn't see CM, like didn't see it down there at all, or couldn't find how to figure out the
No,
angle?
I just didn't see it.
Didn't even see it. So was that the only one you missed? So you're perfect on the ones you did. Okay. Don't overlook things on the test though. Though you won't have a lectern in your way on the test. Chris, now of course we missed that arc up front, right? But after that, of the angles you did, several of them, I was like, okay, your answer would have been this. Most of them correct.
Only missed two.
So we only really missed two. Okay. How many?
So when I put the arcs right, and I went and put them on the circle, I put them on, I had like 40, like for the CF, I originally had like 45. And
So you wrote 40 here, but on the picture you put 45? Oh, so all your answers are going to be 2.5 degrees off, or so, not necessarily even hard and fast 2.5. All right, Genesis.
I messed up on like the ones we have to do, add the two.
Okay, so the ones that were half the sum, the various ones formed at M.
Yeah.
You got all the others, but not the ones at M.
Yeah.
Okay, so again, the key there is finding which arcs are in question, adding them, taking F, and of course your calculator can do that for you. You just have to identify which arcs. Jamie?
I just missed 3, and it was mainly because I was thinking piece of the chord and the tangent at the
Okay.
end there, but I understand now.
All right, Kendall.
I missed BPX.
BPX, that's the one outside. So half the difference. Do you see how to spot the arcs in question? Okay. And then Audrey.
I missed BPX but I subtracted and I just forgot half.
Okay, so you remember the difference, but forgot the half the difference, okay? We're gonna be able to do this tomorrow.
Yep.
All right, we've got about 4 minutes left. That completes the review that I needed to do with you. Questions? Yes, ma'am.
Will there be a proof on the test?
There will be 2 proofs on the test. 2 proofs on the test. It will be similar to the proofs we've done recently that involve arcs and angles, okay? But of course you'll want to make sure you get clangy things like, you know, if 2 chords are equal, arcs are equal, right? 2 chords are equal, the arcs are equal. If 2 chords are the same distance from the center, then they're equal. If a diameter is perpendicular to a chord, it bisects the chord and the arcs. If you got parallel lines cutting through the circle, arcs in between them are going to be equal. Tangent and a radius clang, perpendicular. 2 tangents to the same circle clang.
Equal.
From the same point. 2 tangents to the same circle from the same point, equal to each other. Trying to think of other clanginess that we would have. Yeah, stuff like that there.
Miniature with the ones.
Well, rest, but also skim over those, look over those theorems, 35 to 46, I think I said. You ready for the test tomorrow? We're going to end the video here.